Okay, so very good afternoon, everyone. My name is. Oh, could you please confirm once that I am audible, visible? Just once, please confirm that I am audible, I am visible, as well as you can see the presentation. Okay, okay, fine. Yes, let me share the link also. So I'm going- Yes. So very good afternoon, everyone. My name is Ambuj. I am a research scholar at Agriculture and Food Engineering Department from IIT Kharagpur, and I'll be taking your live interactive session for the course Computer Vision. This course is taught by Professor Jayant Mukhopadhyay from IIT Kharagpur. And what we'll be doing in this particular session is that we'll be solving some of the multiple choice questions based on the previous week's content. Okay, I'll be solving some of the questions based on previous week's content in front of you all. And then after this particular part of the session is over, then I prepared a particular Google Colab notebook which I'll try to show you, and I will try to practically demonstrate some of the concepts related to image processing. Okay, particularly in this session, I'll be telling you about the color image processing, how we are able to segregate different colors. Okay, there are three basic models. First is RGB color segmentation, another one is HSV color segmentation, another one is YCBCR color segmentation. Okay. This type of segmentation models exist, and we'll be demonstrating you all of these. Okay. Through practically through a Google Colab notebook, and you will be seeing this particular concept. Okay. So let me begin the session, and my sincere advice to you all is please take a pen and notebook. At least try to jot down what are the questions, what are the practical aspect, what are the questions, in particular values are there in the question, and how I am approaching it. Okay, that you try to jot it down, and after the session is over, please take the PDF of the session. Okay, and try to numerically solve each and everything. And if any doubt exists, then please ask me in the next session. Okay, so let us begin. Okay, for the very first question. Okay, for questions 1 and 2, consider a pixel P in RGB space, which is given by 100, 150, and 90. Based on the given data, solve the following questions 1 and 2. Okay, question 1 is, what is the corresponding value of the pixel P in CMY space? Okay, and these are your options. Okay, please jot down both of these values. Okay, pixel P, which in RGB space is given by 100, 150, and 190. Okay, and now correspondingly, you have to convert it to CMY color space. Okay, please jot down both the values. Then I'll try to say, okay, how to proceed with this particular question. Okay. Now, if you see here, okay, let me tell you there. Uh, if we are talking about digital image processing, digital color image processing, okay, two fundamental models they exist: a digital color image processing, which is RGB, okay, then subtractive, which is CMYK. Okay. In RGB, your primary color space is limited to red, green, and blue. It is used by your all the devices, as well as if you are watching this particular session on a laptop screen or on a smartphone screen, the both of them use LED diodes. Okay, inside those particular diodes, this particular three from these three particular colors, all the colors are created, which are RGB, red, green, and blue. Okay, you start from black and add the colored light based on the increase in the signal intensity as well as the color which you demand. Okay. Mixing all three at full intensity will give you white. Okay. So three-dimensional vector space would be there. It would be having three particular values. Okay. Of R, G, and B. Okay. Now you try to see this one is additive. Okay. Since you are starting from black, okay, which is having no light, and you are continuing when there is full light. Another color uh, um, system exists which is subtractive. Okay, that one is CMY. Okay, and that is used by color printing processes. Okay, inks or paints. Primary inks are cyan, magenta, and yellow. You start from white and then you try to subtract the light amount of light by absorbing certain wavelengths. Okay, mixing all three these three basic colors, which are cyan, magenta, and yellow, will give you black. Okay. This particular system is used in your printing presses. Okay. And the previous one system is used in your LED devices, in your smartphone screens, in your day-to-day activities. Okay. Now, why CMY is the complement of RGB? Okay. Each subtractive ink blocks the complementary color of the additive model. Okay. Cyan, okay, this particular color C will absorb red. Okay, it will transmit green actually. Magenta will absorb green. It will transmit red and blue. Then yellow will absorb blue. Okay, and it will transmit red and green. Okay. So cyan ink is not red, magenta is not green. Okay, and yellow ink is not blue. Okay, so magenta will reflect your red and blue, but it will absorb the green. Okay. So simple color conversion formula is there. Nothing complication is there. Okay, in your CMY, corresponding to your CMY, there is RGB. Okay. So directly C value you can calculate as 255 minus R. Okay. 255 is the maximum value. Okay. 0 is the minimum value. Okay. So value will get as 255 minus R. Then M value you will get as 255 minus G. And Y value you will get as 255 minus G. Very simple. Okay. 255 is the maximum. Okay. Value of the 8-bit channel. Okay. You have to just subtract this particular number from the value. Okay. So in your case, R, G, and B values were given 100, 150, 90. C value is 255 minus 100, 155. M value is 255 minus 150, 105. And y value is 255 minus 90, which is 165. So same y is 155, 105, 165. So practical notes are there. Okay. In printing, we generally use same by k. Okay. And in professional workflows, you can normalize always by dividing by the largest value, which is 255. Okay. So C value will directly get as 1 minus R, and value is 1 minus G, and Y value is 1 minus V. As well as one gamma correction exists in uh, on screens colors are just one second. Just one second. Yeah. In case of your one, particularly in case of your projecting, okay, in case of your projections which are used in particularly cinema halls and wherever you want to project, okay, then a particular function exists which is gamma correction. Okay. On screens, colors are gamma encoded. Okay, state inversion mainly to linearization. Okay, linearization I have already taught you. Okay, given the session only. Okay, how particular colors are dealt and how linearization that will exist that we have seen. Okay, so if you want to increase the sharpness, you have to go with your gamma correction. Okay, that particular function exists. Okay, then for accurate printing, you have to convert from RGB to CMYK. Ensures what you see on the screen is what it prints on the paper. Okay. Color management in professional design softwares. Okay. For example, your Adobe Photoshop, InDesign, they constantly convert between these particular spaces and they apply profiles for device specific behaviors. So you have to master both additive and subtractive models. Then you can control the color reproduction end to end from digital artwork to powder printed object. Within your digital artwork, RGB color space will work, and within your final printed output, same white will. Moving to the next question, CIE chromaticity model define three standard primaries XYZ that can be added to form all visible colors. Compute the corresponding point for pixel P in normalized XY chromaticity space. Then consider the transformation model as 0.49, 0.31, 0.2, 0.18, 0.81, 0.001, 0.01, then 0.1. Please note down all the values. Transformation matrix already has been given to you. Okay. And chromaticity model has been defined with three standard primaries, which is XYZ. Okay. Okay. Let's move forward. Okay. From RGB to CIE. Okay. Now from RGB to CIE XYZ. Okay. The CIE XYZ, okay, it defines three virtual primaries, which is X, Y, Z, such that any visible color can be presented by a non-negative linear combination of them. Okay. This particular tri-stimulus values are given like this. X, Y, Z is M, R, G, B. Okay. So different type of color models they exist. Along with this, one particular one is CIE XYZ. Okay. M is this particular transformation matrix that has been mentioned in the question. Okay. R, G, and B values, I think directly they have given. Okay. Not directly. Okay. R value. Okay. From question number one. Okay. R value 100, G value 150, B value 90. It has been mentioned in question number one. So x, y, z directly we will calculate. We will try to calculate using this particular matrix multiplication. Okay. Matrix has been provided to you within this particular question, which is the second part of the question. RGB values are from the first part of the question. You just have to multiply both of them. X value you will get as 113.5. Y value you will get as 140.4. Then Z value you will get as 9.6. Okay. Now you have to normalize to chromaticity. Okay. Chromaticity coordinates strip out overall luminescence by projecting XYZ onto the plane. X is given as capital X over capital X plus capital Y plus capital Z. Small y is capital Y over capital X plus capital Y plus capital Z. So x plus y plus z is this particular value, which is 344.5, and you try to divide both of the values, individual x value by this particular sum, individual y value by this particular sum, and you will get as small x as 0.33, small y as 0.4. Then interpretation of the answer. Okay. X and Y locate the U and saturation on CIE 1931 chromaticity diagram. Third coordinate Z is redundant since X plus Y plus Z is 1. And then we will numerically obtain X and Y individually as 0.338. Point. So correct option would be option number D. Correct option would be this particular one. So I hope question number one, question number two, conjunction, there were two questions. They are clear to you. Then the need for universal color space. In case of your every camera, monitor, printer, it has its own gamut, which means the color space model. Okay. That is range of colors it can produce, they vary because light intensity in case of your RGB LEDs, they will vary. If you send any RGB triplet to two different devices, they may run noticeably different hue brightness. For standardization to compare and convert the different colors reliably, International Commission on Illumination, which is CIE, has defined XYZ color space in 1931, okay, 1931 based on human visual experiments. So tri-stimulus values X, Y, and Z are not physical light sources, but they are mathematical virtual parameters. So any real-world spectral stimulus can be measured by non-negative combination of these three primaries. Capital Y was chosen so that it corresponds directly to luminescence or perceived brightness. So from RGB to XYZ, a linear transform. If you know pixels RGB in some device-specific space, you can use a 3 by 3 matrix M to convert it to capital X, capital Y, capital Z, where capital X, capital Y, capital Z will be equal to capital M multiplied by your RGB values, where each row of M tells you how much each device, red, green, or blue, contributes to capital X, capital Y, or capital Z. Different RGB spaces have different capital M matrices tailored to their primaries and void points. So such distinction exists, and you can then see it yourself. Then chromaticity, which is X comma Y, which is stripping out the brightness value. Pure XYZ values encode both hue, saturation, and luminescence. Often you care about the colorfulness, which is hue and saturation, regardless of how light or dark it is. That's what chromaticity does. Small x is capital X over capital X plus capital Y plus capital Z, and small y is capital Y over capital X plus capital Y plus capital Z that you already have seen. Okay. And we solved a particular numerical question also. So small x, small y lies in the 2D diagram. Okay. Every visible hue corresponds to a point. Okay. The boundary is pure, made of spectral colors. The third coordinate is 1 minus x minus y. So only two are. By normalizing, okay, we can eliminate the overall intensity. Okay, those spectral lights of different brightness will uh, will have identical color map. Okay. In any of the color space, they will have the same brightness. That is why we are using this particular CIE. Okay. It matters in practice. Why? Because when you move an image from one RGB space to another, okay, RGB to XYZ to RGB dash or CMYK, okay, then color difference matrices, many perceptual different formulas, start in XYZ or a derived form such as LA star, B star, LU star, V star. Okay. That is why this particular interference or model is required. Okay. Then in case of your device characterization, yes, by measuring how RGB maps to XYZ, you try to build the profiles that in short consistent color. So that is why such distinction exists. Okay. Yes, on CIA chart, Y it sets nearly 0.33. Okay, X and Y values is this one. Okay. And moving outwardly along the color chart, it will give you blues on one side, reds on another side, and all real colors live inside that curve. Okay, mixtures lie on straight lines between their component chromaticities. By understanding this particular CIE XYZ, okay, and its chromaticity projection, the color professionals they try to maintain accurate, predictable color across cameras, screens, and print. Even when those devices speak very different languages or very different brightness level adjustment is there. That is why we try to normalize all of these things. So you must have seen this practical experience even if you go in a 3D cinema hall or you are watching the same movie on your laptop screen, on your mobile screen, the color normalization is there, but your visual experience is different because the cinematography is 3D or 2D based on red. The experience is different, but still the color segmentation is almost the same. That is the reason. Okay. Then moving to the next question. Okay. Which of the following statements are correct? Color captured in the RGB color space. Okay, there is a space here. Okay, it is a space. Okay, space is there are two separate parts. Okay, so color captured in the RGB color space is not suitable for direct interpretation of color components. Image first statement is this. Then CIE chromaticity chart represents colors in a 2D space according to tri-stimulus model of color representation. Or in digital cameras, color images are mostly captured using a CFA or luminescence Y is encoded using less bits than chroming sense values I. So, which of the following statements are correct? This you are yes. Yes. Now you see here the correct answers are A, B, and C. It's a MSQ. Please see yourself in the examination whether it is a MCQ or it is a MSQ. MSQ is multiple select questions in which or more of the options would be correct. Okay. So this one is a MSQ, multiple select question. It's not a MCQ in which single choice would be there. So in this particular case, three particular choices are correct, which are A, B, and C. Okay. How? We'll just see. Statements that are correct are yes, statement number A is color captured in the RGB color space is not suitable for direct interpretation of color components. Yes, definitely. That is why so many color systems exist. And CIE chromaticity chart represents colors in a 2D space according to the prior stimulus model of colors representation. Yes, this particular statement is 100% correct. Then Your C statement is in digital cameras, color images are mostly captured using CFA, which is color filter array. Okay. All these C statements are correct. Okay. For statement one, RGB isn't ideal for interpreting perceptual color attributes because it is device independent. Okay. RGB values depend particularly on red, green, and blue primaries of the camera or display. So no direct mapping to hue, saturation, and luminescence is there. Okay. Human vision, it separates brightness from your color, which is the chroma, okay, or chrominescence. Okay. So in RGB, all three channels jointly encode both. So you can't easily say that this is 60% green in the perceptual sense. Okay. In consequence, for tasks like skin tone detection, white balance, or perceptual color adjustment, one typically first should convert RGB into a more interpretable space, which is essentially CIE, okay, or YCBCR. So chromaticity, CIE chromaticity chart is a 2D projection of XYZ. Yes, CIE XYZ is tri-stimulus. Any color can be represented by three values XYZ, which are device independent. Tri-stimulus responses derived from just be X factors. Okay. So by normalizing, small x is capital X over capital X plus capital Y plus capital Z. Small y is capital Y over capital X plus capital Y plus capital Z. You remove overall luminescence and you get a pure color, which is the familiar shoe shaped CIE 1931 diagram, which you already must have seen within the lectures. So we are just trying to eliminate the component of variation, which is your overall luminescence as well as your brightness, so that we can compare the RGB color space with our own uh, own human color vision system. Okay, so that is the thing. Then digital cameras use a color filter array. Yes, they use Bayer filter. Okay, almost all single sensor cameras place a mosaic of tiny red, green, and blue filters directly over the photo sites. Okay. Then mosaicing as well as demosaicing, each photo site measures only one color channel. So our demosaicing algorithm then will interpolate the missing two channels, okay, per pixel to reconstruct the full image. Okay. So bit allocation and luminescence versus chrominescence. This was your last statement, which is false. Okay. In most of your video as well as image codecs, okay, luminescence is encoded with equal or greater precision than chrominescence, okay, not less. So one particular statement or one particular word is only correct, which is greater. In fact, in chroma, channels are often subsampled, okay, because eyes less sensitive to high frequency colored tone. So this is a very interesting fact that whatever color perception we are having, okay, because all the animals on the planet are not having the same color perception. Okay. So difference in color perception exists for different people or different species. Okay, this is the thing. So yes, in this particular case, A, B, and C are correct, and rest all are incorrect. Okay. Rest all means only statement B is. Okay. So moving forward, yes. Question number four. Consider that the color of the source illuminant is represented by RGB vector space, okay, which is 100, 150, 200. Target color is given by this particular value 50, 150, and 100. And given a color vector 100, 100, 100 in the source image, compute the color corrected vector using diagonal correction. Using the diagonal correction rule, you just have to uh, compute the color corrected vector. Okay, this is the question. Please jot down all the values. Got the RGB vector, got down the RGB vector, then what is the target color space, then what is the color vector which has been given in the source image, and now you have to compute what is the color corrected vector using the diagonal correction tool. So try to jot down all the information that has been given in the question, then we will see the statement. how things will happen. Yes. Now you try to see here the diagonal gain, okay, or the one carries gain. In this particular case, we assume that each channel scales independently by the ratio of the desired to the source illuminating. Okay, so in case of this particular thing, the three particular ratios you can calculate, which is KR, KG, and KB. It is given as ratio of target to ratio of source. Okay, red. What is the color intensity color pixel intensity in red color space? Red divided by red color space pixel intensity in source. Similarly for green. Similarly for blue. So directly, if I'll try to calculate target to source ratios of three particular color pixel intensities in R, G, and B channels, I'll get 50 over 100, which is zero point 0.5, 150 over 150, which is 1, and 100 over 200, which is 0.5. And if you will apply the particular gains directly to your pixel, which is 100, 100, 100, you will get as R dash, G dash, and B dash. So it's nothing but 0 0.5 into 100, 1 into 100, and zero point 0.5 into 100, which is 50, 100 into. Okay. So preserving overall brightness is very, very important. Okay. Often we also want the average or sum of the corrected channels to match that of the original. So the image doesn't look too dark or too overall bright. Okay. So original sum is S, which is R, G, and B. Sum of all these three values, which is 100, 100, 100, which is 300. Okay. Post gain sum is S dash, which is kg, KR into R, kg into G, plus kb into D, which is zero point 0.5 into 100, 1 into 100, or zero point 0.5 into 100, which is overall coming as 200. Okay. Force the corrected channels to somewhere to S. We get reduce a global scale factor, which is S over S dash, which is 300 over 200, which is 1.5. Then you try to calculate what is the final brightness is corrected. Okay. So that is individually in case of your R, G, and B values, it is calculated as F AR into R. Okay. So R, G, and B directly we have seen that is 100, 100, 100. F we have calculated 1.5, and KR, KG, KB ratios we have calculated as 0.5, 1, and zero point 0.5. And if you will multiply all the particular values, you will get the final output as 75, 150, and 75. So 75, 150, and 75 that will give you choice D. Okay. Why the normalization step? Without F, the simple per scale scaling makes the overall image darker. Some drops from 300 to 200. Okay. And with F, you maintain the original energy or the total brightness, ensuring that white stays neutral and at the same perceived intensity. So two-step process is there. First of all, you have to calculate the per channel diagonal gain. Then you have to calculate a global normalization. Okay. And then you have to calculate the one carries white balance terms. That is the thing. Then white balance, this can be thought of as undoing the color cast imposed by seen illuminant, and so that neutrals will be seen. Okay. Which are white paper or the gray card will appear match a neutral. in your image, the diagonal correction rule, okay, or simpler implementation of the one carries adaptation model does this in two particular stages. Okay, imagine your source illuminant as RGB spectral strength S as SR, SG, and SB, and you want to look like the target illuminant. Okay, ER, TG, and TB. Then one carries the assumption. You will calculate three particular scalar gains KR, KG, and KB, which is PR over SR, TG over SG, and TB over SB. These gains will tell you how much to amplify or attenuate each color channel so that the source white maps to the desired. Then applying gains to every pixel, RG and B, P dash, AR, R into R, KG into G, and KB into B. Then Y diagonal, because if you write this as multiply matrix, so it's diagonal KR, KG, KB. Okay. So brightness preservation or your global normalization, if you only apply the per channel gains, you often end up with a different overall luminescence. For instance, your neutral gain gray, which is 100, under gains, which is 0.5, 1, and 0.5, it becomes 50, 100, and 50. So these particular components, okay, some of the components is 200, which is lower than the original sum. And then you try to introduce a global factor, which is a RG&D divided by KR into R plus KG into G plus KB into B. Okay. That has to be computed once, and then you have to compute the final corrected pixel. Okay. FKR into R, FKG into G, and FKB into B. This will ensure that the neutral gray stays at the same overall brightness, preventing the image from becoming too light or dark after the white balance is. Why it will work and what are the limits? Simplicity and speed. Okay. Only four scalar multiplications per pixel, which are three channel gains from global. Okay. And very efficient, which is easy to implement in hardware or real-time pipelines. What approximation? A humanized chromatic interpretation roughly behaves like per cone gain adjustments under many typical lightning changes when it works well for daylight versus your tungsten or fluorescent light. Limitations are no cross-channel correction. Okay. If your camera's red sensor leaks into green, or if the illuminant has very weird spectrum, then your digital diagonal model can't fully compensate it. Nonlinear pipelines. Okay, in practice, you apply the gamma correction, tone curve, color matrices so often that you want to diagonally correct, okay, or linearize the domain. Then spatial variation. Real scenes may have multiple light sources. One global gain may under or overcorrect. something. Okay, these are the particular limitations. Putting all the information together, which I have just talked about, okay, you have to measure or estimate your source illuminant, specify what is your target illuminant, then you have to compute the gains, AR, KG, and KB, and you have to transform each pixel, which is given in RGB color space, to the desired pixel, which is FKRR to R, FKG into G, and FKBB into B. Okay, the two-step diagonal plus normalization workflow is the backbone of nearly every automatic or manual white balance routine in your system. And question number 5, please jot it down. Interpolate G5. Okay, interpolate this particular component G5 using Laplacian corrected edge correlated interpolation using given Bayes pattern. Particular Bayes pattern you have been given, okay, corresponding CFA values that have been mentioned here, okay, and you have been asked, okay, try to uh, calculate or interpolate the G5. G5 you just have to calculate or interpolate. Yes. Now you try to see here. Okay. First of all, the Laplacian corrected patch correlated interpolation for missing green samples, which are either blue or red. They are designed, they are designed to avoid smoothing across edges. Okay. So you don't blur true color image boundaries or inject high frequency detail using the Laplacian or other other channel to preserve the texture. Okay, how it will work? We'll just try to demonstrate. Okay. First of all, you have to identify all your neighbors. Okay. Horizontal green neighbors are G4, okay, and G6. Then your vertical green neighbors are G2 and G8. Okay. And blue neighbors are B3, B7, and your vertical neighbors are B1 and B9. Okay. First, we have identified all the geographical neighbors. Okay, identifying the neighbors. Then you try to compute the directional variation measures. Okay, we found two particular matrices, which is del H and del V. Del H is B4 minus G6 plus B5 minus B3 plus B5 minus B7. Okay, and del V is G2 minus G8 plus B5 minus B1 plus B2 B5 minus B9. Okay. So plugging in all the values. Okay. G4 is 65, G6 is 125. So modulus of 65 minus 125 is 60. B5 value is 100, B3 value is 18, B7 value is 150. So you try to compute uh, what particular value it is coming. Delta H will come as G4 minus G6. That value particular one is 60. And the next term B5 minus B3 plus B5 minus B7 we have computed as 32. So 50 plus 32 is 92. Then G2 and G8 have been given in the numerical itself. Okay, we have identified as 85 and 85. 85 minus 85 is 0. And B1 value was 25, B9 value was 35. Okay, so computing the expression, second part of the expression of the del V. Okay, so del V value would be 0 plus 140 because G2 minus G8 is modulus of 85 minus 85, that is 0. And this next term, which is B5 minus B1 plus B5 minus B9. Okay. That we have tried to compute as 140. So since del H is less than del V, so local image edge is stronger in the vertical direction. We will interpolate along the horizontal to avoid the crossing of across the vertical edges. Okay. So from your interpolated values, okay, G5 will be nothing but G4 plus G6 divided by 2, that is base average along the horizontal. And next term will be B5 minus B3 plus B5 minus B7 divided by 4, which is your Laplacian sample. So base average value that is coming as 95 and Laplacian correction is coming as 8. So G5 is coming as 95 plus 8, that is 103. Why this will work? Because by comparing del H versus del V, you try to avoid interpolating across the strongest local edge, preserving your sharp boundaries. And your Laplacian term, it injects a bit of high frequency detail, okay, from blue channel into the green channel estimate, okay, which helps maintain texture rather than over smoothing. So why we are doing this? For edge aware, okay, Laplacian character interpolation that will combine best of both smooth averaging, which will reduce the noise, as well as we'll try to preserve the details even. Oh, this is the I hope this particular one is clear. This is a bit detailed question. Please revise it. Okay. The correct answer is 103. Yes, in itself it was 103. We are also getting the same. Okay. Please revise this particular question at least after the session is over. Okay. Take the PDF, jot down all the particular values. Okay. And then try to revise whatever the information that has been shown today. Okay. Then moving forward to the next question. Okay. In a simplified chromaticity triangle, the primaries have coordinates R, which is 0.6, 0.3, okay, D, which is having coordinates zero point 0.2, zero point 0.7, B is having coordinates 0.15, 0.10, white point is W equal to 0.33, 0.33, okay. Sample chromaticity is zero point 0.4, 0.35, okay. If you move Q radially away from W to the gamut boundary, okay, which of the following first intersection you will encounter? Or what is the point of maximum saturation that has been asked in the question? Okay, please try to jot it down. Okay, yes. Now, if you see here, okay, correct option would be A. We'll just try to see it in detail. Okay, first of all, you have to write the ray from white through Q. Okay, which is W plus T bracket starts Q minus W. Okay, so W value has been given as 0.33, 0.33. T value, okay, that we just have to write it down as it is, and then Q minus W. Q value has been given as zero point 0.4, 0.35 Q value, and W value is again 0.33, 0.33. So the equation LT will reduce to 0.33, 0.33 plus T 0.07, comma zero point 0.02. In your parametric form, your XT will be 0.33 plus T multiplied by 0.07, and YT will be 0.33 plus 0.02 T. Edges of the triangle RG between R and G, GV between G and B, and BR between B and R that we have to compute. Okay. Testing the intersection within each edge by solving for T and checking if the resulting point lies between the two vertices. RG edges line along line through R, which is zero point 0.6, zero point 0.3, and G is zero point 0.2, zero point 0.7. Solving this particular equation, 0.33 plus 0.07t and 0.33 plus 0.02t, you will get as 1 minus alpha 0.06, comma 0.30 plus alpha 0.20, comma 0.7 for some t greater than 1, and alpha will belong to the closed interval 0 to 1. Then you try to equate both of the components. 0.33 plus 0.07t is 0.60 minus 0.40 alpha. Okay, and 0.33t plus 0.02t is zero point 0.3 plus 0.40 alpha. And from here, you try to compute, uh, you try to add both of the equations. Okay, adding both of the equations, LHS and RHS respectively, you will get T from one of the equations, 0.66 plus 0.09t equal to 0.9. So P value will get us 2.667, and X value will get us 0.52, Y value will get us 0.38. So alpha value, you try to see here, 0.60 minus 0.52 divided by zero point 0.4. Okay. So directly, you will get alpha from both of the equations same as zero point 0.2. Okay. So in case of your GB edge, you would solve for similarly because the ray is pointing mostly towards the red, it will hit the RG edge before GB edge. So the ray first intersects the RG edge at approximately 0.52 and zero point 0.5, 0.38. Okay. So the only answer which is close to that is A, which is 0.5 to 0.28. Okay, that is approximately coming the value. Okay, Y value is somewhat different. Still the correct option if you want to mark it as A1. That is the thing here. That is the concept involved. Okay. Chromaticity and the CIE XY plane, the tri-stimulus. Okay. For chromaticity in your CIE XYZ space, color XYZ is found out by normalizing small x as capital X plus divided by capital X plus capital Y plus capital Z and small y as capital Y over capital X plus capital Z. We try to remove overall brightness, which is the luminescence, try to retain only U plus saturation. Okay. Every visible U plus U and saturation lives inside the spectral locus or shoe. So y, x and y, x, y, okay, x and y tell us where on the chromaticity chart a color lies. Third coordinate z equal to 1 minus x minus y is redundant. So devise gamut as a triangle of primaries. Okay, in case of your printer gamut, okay, any printer will try to reproduce the fundamental colors which are R, G, and B. Okay, red, green, and blue. In XY space, those three primaries appear as 3 points R, G, and B. Okay. Convex hull, yes, all mixture chromaticities lie in your convex hull triangle, okay, which is formed by these 3 points. That is divides gamut. Okay. Okay. Colors you can display also. Okay. Then the white point, okay, what would be definition? The white point W is the chromaticity of neutral, okay, equal energy or devices neutral gray. Anchor for U. U is measured as the direction from white to your sample in XY space. So if you move directly away from W, you follow the same perceived U, okay, or which you just change the saturation. Then U ray or the radial line from white to your sample space. Okay. The geometric idea is to change the saturation but not the U value. Okay. Along the straight line that starts at W and passes through your sample, which is at Q. So that is why in parametric form this particular equation exists, which is W plus T that starts Q minus W equal to 0, you would be having white. Okay, and at T equal to 1, you would be having your original space. And we are trying to linearize our entire. Okay. Next, what is the boundary, gamut boundary, as well as the maximal saturation? Okay. The maximal saturation, okay, the furthest point along LT that will still be inside the triangle RGB in your maximum saturated color of that U. Okay. And which edge you have to just cross, which is can be either RG, it can be either GP, or it can be either BR, that you just have to randomly select. Okay. Run across all of the three particular edges and you try to intersect and then you try to algebraically calculate the results. So parametrically you have to write the LT equation, then you have to write each edge as 1 minus alpha T start plus alpha T end, okay, where alpha belongs to closed interval 0 to 1, okay. Then equate coordinates and solve for T and alpha. Then keep only the solutions with T greater than 1 and alpha belonging to closed interval 0 to 1. And then you try to projective uh, uh, homogeneous cross products. You try to calculate. Okay. Flip each x comma y, okay, as x comma y comma 1. And the line so P and Q is LPQ equal to P cross Q. And intersection of two lines L1 and L2 is L1 cross L2. Okay, and convert result U comma V comma W back to U by V or V by W. Okay. And discard whatever the intersections are there that lie outside the terminal. Then yes, you have to check the validity also. Even if two infinite lines intersect, the point might lie outside the finite segment, and check the resulting x comma y falls between the two edge endpoints. And your positive t, okay, you want intersection beyond, not the trivial one, between w and q. Okay. So two answers could arise. In some formulations, you need to record every intersection of LT within the gamut boundary. Okay, if the ray enters the triangle on one side and exists on the another, then you may get two max saturation points. Both lie at the same view but on different edges. And in case of our MCQ, we found out that the ray from point 33, okay, from point 33 to point 4 and point 35, we just try to find out the ray. Then we checked it across each edge. It did not intersect B comma B in segment. Okay, it did hit RG first, and that gives our option A. And then we need to extend it further. It could also hit with D comma R. That in case of your string cross. Okay. So bottom line is this one, that chromaticity will strip out the entire luminescence, and the gamma triangle constants where you can just try to go. U ray that fixes the direction, and edge intersection will lead to maximum saturation. This is the entire gist of the talk sign that just. So yes, please try to jot down this particular Bayes pattern. A particular Bayes pattern has been given, and corresponding CFE values are there. So based on the given information, you need to solve the question number 7 and 8. Question 7 says, using interpolation by averaging red and blue hues, compute the G here. This you just try to calculate what is the G8 values, and then I will just see you in a minute. Okay. Yes. Now we'll try to see a particular Bayes pattern has been given. Okay. And you have to compute the corresponding CFA values based on the given information. You have to solve the questions 7 and 8. Okay. So first of all, you have to interpolate by averaging red and blue hues. Okay. Okay. In case of your Bayer mosaic, at every blue or red pixel, the green component is missing and must be interpolated. Simplest and still quite effective approaches bilinear interpolation of green. Okay. Average the four nearest green samples. Okay. From north, south, east, and west. Okay. So you want G8. Okay. Missing green at the blue pixel, which is B8, I think. Yeah. So locate the four green neighbors of B8. Okay. So north of B8 is G3 and south of B8 is G1. Okay. G1 3. Okay. And B west of B8 is G7 and east of B8 is G9. Okay. So all the values you try to just see and then you try to plug in the values using bilinear interpolation formula. Okay. Bilinear green at the blue pixel is average of four orthogonal green neighbors, which is G3 plus G13 plus G7 plus G9 divided by 4. Okay. That is G8. So using the bilinear interpolation formula, you will get G8 as G3 plus G13 plus G7 plus G9 divided by 4 and plugging in the numbers G3 as 18, G13 as 150, G7 as 25 and G9 as 45, you get G8 as 59.5. Okay. The final answer is G8 as 59.5. And why this will work? Because green channel is having the highest sampling density in a Bayer filter, and bilinear interpolation is the simplest agonistic method. Okay, even if it is good, if you haven't detected the edges yet. Okay, so this is the most advanced demosaicing. Okay, mosaicing and demosaicing, both of the concepts, very important in order to create a 3D depth image from 2D raster images. Okay. So most more advanced demosaicing would adapt the interpolation direction to local edges, but bilinear is often the first step or the baseline. Next, question number 8, which is a multiple choice question. Okay. Using simple bilinear interpolation, compute the missing red value. Okay, red value is nothing but the pixel value at G7. Okay, G7 value. Okay, row 2 and column 2, this particular one. Okay, that you have to compute in the Bayer array. Okay, this particular value you just have to compute. Okay. And options has been already mentioned within this particular question. Okay, try to jot down what is the Bayer pattern and what is the CFA values that have been given, and a particular one value, which is the missing value, you have to compute. Already we have seen this particular methodology in two successive questions. You just have to apply within the same methodology within this question only. Okay. Yes. Now you try to see. Okay. G7, the at G7, the red channel is missing. Okay. D7 in the blue row, okay, is two nearest red neighbors. They will lie vertically at R2, which is 14, and R12, which is 45. Then you try to compute R7, which is R2 plus R12 divided by 2. Okay. So first of all, you have to identify D7's the red neighbors. Okay. On row 2, okay, it's on row 2. So red pixels will appear immediately above and below. R2 is 14 and R12 is 45. Okay. And using the bilinear interpolation, you will get the option as 14 plus 45 divided by 2. Okay. That is 59 by 2, that is 29.5. So that will be option B. Okay. 14 plus 45, these two values, okay, divided by 2. Okay. 1 second. Yeah. 14 plus 45 divided by 2. Okay. Directly we have just seen, okay, how the particular averaging we are doing and how we are getting the particular values. So next question, which of the following statements are true? Image reconstruction using color demosaiking lead to sharp edges in an image, and green channel is less likely to be aliased. Or in CFA, green channels are sampled at a higher rate than red and blue, and high correlation between red, green, and blue channels are very likely to have similar texture and edge locations. Okay. Which of the following statements are true? That you have to just, yeah. Okay. And it's an MSQ. Okay. Reminder is this, that don't take a single statement. There may be a single statement, or there might be multiple statements also might be correct. Okay, in this particular case. So single statement might be correct, or more than one statements also might be correct. Okay. Yes, in this particular case, B, C, and D. Okay, all the three statements are correct. Okay. Statement A was image reconstruction using color demosaicing. Okay. It leads to sharp edges in an image. No, this is not always true, because demosaicing tries to reconstruct the full color images from sparse samples, which can also lead to blurring or artifacts around edges. Okay, especially in naive or simple methods. Okay, in case of your bilinear interpolation. Okay, so advanced edge-aware demosaicing method aims to preserve edges. Sharp edges are guaranteed, hence this statement is particularly not true always. Statement A is false. Statement B was green channel is less likely to be aliased. Yes, this statement is true because the pair pattern samples the green channel more densely, appears in 50% pixels versus 25% for red and blue. So it will reduce aliasing, okay, because the higher sampling helps preserve high frequency detailed better. Okay, this is true. Then statement C is in CFA, green channels are sampled at a higher rate than red and blue. Okay, yes, this is true. The Bayer pattern uses two green pixels for every red and blue. This is based on the fact that human eye is more sensitive to luminescence. Okay. Luminance, okay, which is heavily influenced by green. So green has to be sampled more densely for being appealing to the human eye. Okay. As well as in your statement D, it was high correlation between red, green, and blue channels are very likely to have similar texture and edge locations. Yes, this particular statement is true. In natural images, the R, G, and B channels are highly correlated, especially in your luminescence regions. Thus, edges and textures tend to align across the channels. This is often used in edge-aware demosaicing techniques. Yes, this particular statement is true. Hence, your final answer is correct options are B, C, and D. Okay, A is not necessarily true. B is true. C is true. Okay, B is true because due to higher frequency of sampling frequency of the green color. C is true because green is sampled more frequently in their CFA. Okay, D is true because color channels tend to have correlated edge structures. So final correct options are B, C, and D. Next is given Bayer pattern. Okay, Bayer's pattern has been given. corresponding CFA values have been given, you have to interpolate R17. Okay, R17, you just have to try to interpolate. Okay. Try to jot down the Bayes pattern as well as the corresponding CFA values. Then we'll just try to see how we can interpolate the value R17. Direct using bilinear interpolation that we just have did. Okay, just we have performed this particular bilinear interpolation. We'll perform it once again within this particular question, and then we'll try to see how it is. Okay. So R17, okay, using the bilinear interpolation, we need to follow these particular steps. First, you have to understand the Bayes pattern, okay, which is has been given already in the question. Okay. Now R17 is row 4, column 2. Row 4, column 2. Okay. That is the location of R17. Position of G17 is row 4, column 2. So R17 is missing because G is encoded here. We want to interpolate using the nearby red pixels that have been given to us. And I think you are clearly able to see that R12 and R22 has been given here. Okay. So to apply bilinear interpolation, we need to use the red neighbors, okay, that are horizontally and vertically aligned. Okay. So G17 is at row 4, okay, column number 2. So R12 is 45, okay. R22 is 225, okay. We also check horizontal neighbors. None of R16 and R18 are red, so they are only the pixels, okay. R12 is 45, R22 is 225. Okay, using the bilinear interpolation. Okay, R17 is R12 plus R22 divided by 2, which is 45 plus 225 divided by 2, that is 270 divided by 2, that is 135. Okay, so final answer that we'll get is simple 135. Okay, we are interpolating the value R17 using the two nearby pixels, okay, which were there at the location G17. Okay, that is nothing but R12 plus R22 divided by 2. Okay, so that is 45 plus 225 divided by 2. That is nothing but 25. So this is regarding the 10 questions which I wanted to just discuss. Okay, with you all. Next, in the next part of the session, I'll be moving to my second screen, and I'll be sharing some of the very practical aspects, okay, regarding the image processing, color image processing. We'll just try to see. Okay. Let me unshare this screen. Then I'll be sharing my another screen. Just wait for a minute. Let me also share the PDF files. Okay. The first part of the session is over, where I told you the 10 questions which I wanted to discuss with you all. Okay. The next part of the session, I'll just try to practically demonstrate some of the principal concepts related to theoretical concepts that we already have discussed within our this particular lecture only. Okay. Let me share my entire screen with you. It's an issue with my mouse here. Now I think everything should be perfect. Okay. Let me share it with you. Yeah. Okay. So you first things first. Okay. Okay. First things first. Let me first tell you. Okay. Let me first tell you about the RGB color model. Okay. The RGB color model. I'll just try to demonstrate it first. Okay. First things first. I hope the screen is visible. Yes. So in case your 1 second, let me maximize this. Is it's fine. Yeah. It's an additive model. Okay. R, G, and T, both all of these values. Okay. In sync. Okay. They have to be done in sync. Okay. R, G, and D, these three pixel values in sync have to be added in order to give you the primary, in order to add these three R, G, and D different color values have to be added, okay, in order to give you a full color image. A full color image would be having all of the three principal components, which are R, G, and D. Okay, all of the three particular components R, G, and D will be present inside an image. That is why an colored image is always a three space vector. Okay, this is one thing. Okay, main purpose of RGB color model is for sensing, representation, display of images in electronic systems, television, computer that you can see. It's device dependent. Okay. RGB color space modeling. It is device dependent because, as I told you, there various limitations exist. Okay. Various limitations they will be existing. Okay. In case of your RGB imaging. Okay. Limitations. What is the form and manner of the limitation? Because first of all, you try to understand that the device capability is limited. Okay. Device capability. What is the meaning? That the projective spacing of a certain pixel intensity value would be different. Okay. That is the thing. For different images, for different devices, there the potential of projecting a particular pixel value that would be very different, and that output would be very very different when you will try to compare with other parameters which are brightness, which are luminescence. Okay, so if you will try to compare with those particular values, then you will be able to visualize very well that the projective imaging, okay, that is very very different in case of your all values. Okay, so that you just try to see. Okay, so RGB is device dependent color model. Okay, different devices detect or reproduce a given RGB value differently. Okay, Since the color elements such as phosphors, dyes, and their response to the individual red and green and blue values levels vary from manufacturer to manufacturer. Okay, so it is kind of a color management. Okay, so it does not define the same color across devices, but without some kind of color management. Okay, so typical RGB input devices are TV and video cameras, image scanner, digital camera. Okay, so RGB output devices are TV sets of various technologies, CRT, LED, LCD, plasma, OLED. They would be having different projective capabilities. And at the intersection, you try to see this particular diagram, R, G, and B. Okay. They would be adding to make different colors. And if you will try to mix all of these values with same pixel intensity, then you will be getting what? White. Okay. You will be getting white. So this was regarding your RGB color spacing. Okay. What is the physical principles of the choice of red, green, and blue? Okay. That you try to see here. Then history that has been mentioned in this particular open source web page. Okay. This is a Wikipedia web page only, as well as CRT, how particular uh, using the cathode ray tube. Okay. This CRT monitor, how it works cutout as well as the different functionalities and how we are able to reproduce different colors that has been mentioned. Okay, so this was regarding the basics, and this is the numerical representation of the different colors. Okay, in RGB color modeling, this is the representation of different uh, colors. Okay, this particular representation exists of different colors in your hex code table. Okay, different hex codes exist, and this one is the table and how you can interpret in different channels. Okay, 8-bit channel, 12-bit channel, 16-bit, 24-bit, 34-bit channel. The number of channels you will be increasing, the greater would be the RGB tripleting, and greater one would be your uh, pixel intensity values. Okay. So this one is here regarding your color depth, color web page design, color management. Okay. The next color model is HSV, hue saturation value model. Okay, two particular models, hue saturation and lightness, or hue saturation and value, that have been mentioned here, and very beautifully they have shown. Okay, what is the concept of lightness, how it will impact the saturation, how it will impact the hue. Okay, how HSV saturation exists, how saturation will impact the value, how it will impact the hue. Okay, this particular image, the distinction is like mentioned here. And what are the basic principles? What is the when you are increasing hue, what particular thing is increasing? Okay, that you can see when you are increasing saturation, what is increasing? When you are increasing lightness, what is meant by it? That is very beautifully they have demonstrated. Okay, as well as in this particular bicone they have made. Okay, what motivation exists? Try to see here. Okay, and how they have just mentioned it, the hue, radiance, luminescence, luma, brightness, okay, colorfulness, chroma, saturation, as well as hue and chroma, okay, lightness, saturation, okay, these all are there, as well as software interface they have prepared. What are the advantages? What are the disadvantages? Where they can use this particular very distinct image they have used to demonstrate the particular color photograph in RGB. Then they have used the L star color modeling. Then they have used Luma Y star Y modeling, and then they have demonstrated using HSV, using V, and then HSL. And these particular things they have tried to manipulate, and then they have tried to demonstrate how these things. Now, this particular one is the color photograph, then HSL, HSVU, then U shifted, but L star is kept as original, and U shifted, and the CIELCHAB color space is shifted by minus 30 degree, this particular one. What is the color conversion formula to RGB? Okay, HSL to RGB, then HSV to RGB. They have shown here in this particular slide. Okay, try to go through this. This is a very interesting web page, okay, which I found, wanted to share so that you can also get a taste of things in different colors. Okay. Then another model which is YCBCR. See, this is the visualization of YCBCR, color space modeling. Okay. Y is the luma component and CB and CR are the blue difference and the red difference in the chroma components or the color components. So YCBCR model, yes, it exists. And what is the rationale? Black and white televisions in wide use were there before color televisions. Okay. Number of TV sets were there and cameras were there. Some form of backward compatibility they need to have. Okay. So that is the chroma subsampling method that they have used. Okay. So next you try to see conversions. Okay. RGB conversion, RG dash, R dash, G dash, B dash to Y dash, PR, and then these particular conversions. Okay. Then what is the another conversion? CIE conversion we already have seen within this particular session. And then this another standard is there. Okay, ITU RBT dot 709. Okay, this conversion you try to see. Then there are the different things. Okay, different conversion comparisons. Okay. Yes. Then what are the approximate 8 bits for BT.601? Okay. Pixels and different color concepts are there. Try to go through them, but at least have a basic idea what is color conversion, what is different methodology, and when I am changing a particular thing, from along with YCBCR and what I meant, I generally mean through it. Okay, so that you try to see here. Okay. Next, moving forward. Okay. First of all, this is the notebook which I have prepared. Okay, I'll rename it here. This is how you can rename it. First of all, you have to connect to a runtime. Okay, change runtime type. Then since it, or if it is a heavy notebook, I'll go with GPU. I'll also demonstrate. Two GPUs are there. Okay, new versions are coming in this collab. Okay, so V5 E1 is the latest GPU. Okay, that you can also connect. Okay, runtime version you can change here. Here I will only go for CPU because it is a simple task. Okay. Now, what is color image processing? This notebook will try to explain you. And first of all, let me run all the cells. Okay. In time I have selected, then it is time to connect. Okay. After connecting, okay, after it is connected, then we will just try to see what the notebook tries to say. Okay. Let me run all the cells. Yes, all the cells have been ran here. Okay, and the results are already there. This notebook will try to explain the concept of color image processing. You will try to learn how color images are represented, how you can manipulate them, how you can apply basic processing techniques using Python libraries like OpenCV or Matplotlib. So, what is color image? Color image is made up of pixels, where each pixel is represented by multiple values that correspond to different colors. Most common format is your RGB, red, green, and blue format. Okay. Each pixel is represented by three values corresponding to red, green, and blue pixel intensities. You have to mix the pixel intensities, the values ranging from 0 to 255 for your 8-bit image. And by mixing these values, you can represent millions and trillions of colors. So, in case of your RGB, first of all, basics first. Pure red color is represented by 25500. Pure green color is represented by 02550. Pure blue color is represented by 00255. Pure white is 255, 255, 255. Pure black is 000. And the libraries which I have used is OpenCV. First of all, I have used it. Okay. OpenCV or CV2 for image processing, Matplotlib for visualization, NumPy for array manipulation. These particular libraries I have used. First of all, you have to do the loading of the image. Okay. You have to import the libraries. Okay. Import all the libraries. Then on the particular URL, okay, you have to download the image from the URL. Okay. Then you have to convert image from BGR to RGB format. Okay. Then display this particular image. Original image is this one. Okay. Then displays RGB channels separately. This particular image would be having all the three channels. Okay. It is why it is appealing in this format manner. Okay. So we'll try to just uh, segregate all the channels. For the segregating the three channels RG and V, I have used this particular command which is cv2.merge. Okay. So cv2.merge and try to see here in this particular thing. I have made R00, then I have made 0G0, then I have made 00B. So this is regarding R, G, and D segmentation. So in case of your red channel, you will have the output like this. In case of your green channel, you will have the output like this. In case of your blue channel, you will have the corresponding output like this. Then converting it to grayscale, you just don't have to do anything. Okay. And remember always, okay, save the input image in a particular standard format only. Okay. So here I have taken the input and I have saved it as image underscore RGB. So you try to do the same. Then try to do the corresponding manipulation. Gray image equal to CV2 dot CVT color and image RGB, comma CV2 dot color RGB to gray. This manipulation you try to do. Then display the grayscale image plot.im show and CMAP as gray. Okay. If you will try to select those, then you will get the grayscale image like this. Okay. Now for histogram equalization on your grayscale imaging. Okay. First of all, you have to apply the histogram equalization. Equalized image would be CV2 dot equalized with gray image. Okay. Then figure axis is plot dot subplot 1 comma 2. Figure size is 12 comma 5. Okay. Then original grayscale image you try to see, and then histogram equalized image you try to see here. Okay. Then histogram equalization can also be performed on your color images. Okay. Here we will use YCRCB format. Okay. So image YCRCB, that would be nothing but RGB to YCRCB. That is already a function. Okay. And how the particular conversion is there, please try to go through this particular function. Okay. This RGB to YCRCB, this particular function, you try to go through it, and then you would be able to calculate gather what are the different format manner possibilities. Then you have to split the channels. YCRCB is equal to CV2 dot split image to YCRCB. Okay. So you try to apply the histogram equalization to the Y channel. Okay. Histogram equalization you try to perform. Then merge back the channels. We do CV2 dot merge. Okay. Then convert back to the RGB. Okay. Image equalization RGB is image CV2 dot color YCRCB CB to RGB. So try to convert back the image and display the original on the equalized image. Okay. Original color image is this one. Histogram equalized image is this one. Then, as a summary in this notebook, we have covered what is color image, how it is structured, what is RGB color space, how to visualize channels, how to convert to grayscale, how to perform histogram equalization, how to use the OpenCV and Matplotlib libraries to process and visualize the images. This is the foundation for various advanced image processing tools like your filtering, like your edge detection, like your object recognition. Okay. So As an assignment, you can feel free to explore through other color spaces like HSV, LA star, B star, okay, and experiment with the enhancement techniques also. Then, uh, in your color image processing as an extended example, we will cover what is loading an image from URL, then displaying the image and its channel, then enhancing the brightness, applying a color filter, then histogram equalization for better contrast. Okay. So typical example scenario is first of all loading the image. Okay, this particular one is the loading of image. Then you have to set up the request. Okay, then you have to download the image from URL. Okay, convert from RGB from BGR to RGB. Okay, then display the image. Okay, this one is the original image. Same steps I have followed. Then increase the brightness. Okay, sometimes images are too dark. They need to be brightened. You will increase the brightness by adding a constant value to all the pixels. Okay. So here I have taken the arbitrary value as 50. Okay. You can take any of the value and try to experiment with it. Okay. Here in this particular case, I have taken the value as 50, 50. Okay. Let me just try to see here. So increasing the brightness by adding a constant value, brightness value would be equal to 50. Bright image would be equal to CV2 dot add image RGB brightness value, and brightness value, comma 0. All the pixel intensity values I have increased by a single value, which is 50. Then what is the original image and what is the brightened image that we just have seen? Then you try to apply a red filter. Create a red filter by enhancing the red channel. Red filter is image.rgb.copy. Okay. We're displaying original and red filtered image. The original image is this one, red filter image is this one, and then you have to use the dot show. Then program equalization for contrast enhancement. Okay. Histogram equalization is a particular technique that we'll try to apply again. Okay, for luminance channel in YCRCB space. How I have done this, you just try to see here. Image YCRCB equal to CVT CV2 dot CVT color image RGB CV2 dot color RGB2 YCRCB, then splitting all the channels. Okay, Y channel, then Y equalization using this particular function, which is CV2 dot equalize histogram. Okay, this particular function I have called, then I have merged all the channels. Okay, then converting back to the RGB. Okay, that is CV2 dot CVT color. Okay, CV2 dot color YCRCB. Okay, to RGB. When displaying original and equalized images, so what is the original image, what is the histogram equalized image that you have seen. Okay. Then summary of the typical example is how to safely load an image from URL, how to increase brightness for better visibility, how to apply a color filter. Okay, that we will see how to apply a color filter to highlight certain regions and how to enhance contrast by using the histogram equalization in YCRCB space. Okay, that we have seen. So using these techniques, you can improve images under poor lighting conditions. You can highlight objects of interest. You can enhance features before further analysis. You can also experiment with all these features and you try to build more advanced applications. This one was a summary for the second application. Now coming to your third application, it is somewhat different. Here I have used a particular library which is i5 widgets. This particular library is used for making a widget or a slider. This particular slider, what it will try to do, this particular slider will try to increase or decrease the brightness. And how I have done it, you can just see there. Okay, using first of all, I have loaded the image. Okay, same image I am using. Okay, dog face in that particular image I am using. Then I am using image array as mp.array. Okay, then image as cv2 dot and decode, then image rgb as cv2 dot cvt color. Okay, color bgr. RG. So these particular libraries are there. Okay, this particular format manner is there. Then this is the IPy widgets. Okay, using this IPy widgets library, I have dynamically adjusted the brightness of the image, and I have shown you how it changes within the real time. So try to see here. This particular is the function. Okay, and then I have used this create slider. Okay, for brightness adjustment. Okay, so brightness is coming as here. You can see interactively you can change the brightness. This is 0, then this is negative 100, then this one is positive 100. This is how it is. So this is the thing, adjusting brightness. Okay. Then working with HSV saturation color space. Okay, hue saturation value. It will have color space, color information from intensity, making it easier to manipulate aspects like the saturation and brightness. So image HSV is CV2.CVT color. Okay, CV2.color RGB to HSV. That particular image conversion we are doing. Then we are splitting the channels in different HSV as CV2.split. Okay. Then use saturation and value channels. We try to split HSV gray. Okay. And then U channel, saturation, then V channel or value channel. Okay. So after the particularly we have separated U with saturation and value, we have got a number like this. Then for your L A star B star, okay, for LAB, which is separating lightness from the color components A and B. We just try to see here, this is the lightness L, and A channel is like this, and B channel is like this. Okay, this is the separation. Okay, that you can just do yourself. Okay, then real world example is nothing but your standard Haar cascade classifier for face detection. This you can use. Okay. Then convert first of all the entire image to grayscale image. Okay. Then detect face using your R cascade classifier. And here, of course, it is not a face, so no face would be detected, hence it is showing face detected equal to 0. Then medical image enhancement is like this. Original medical scan is this. Enhanced medical scan is like this. Okay. So medical image equal to CV2.CVT color. Okay. CV2.color to RGB to gray. Okay. Then histogram equalization is there. Okay. CV2 dot equalize histogram for medical image. Okay. This particular one image. Then displaying the original and enhanced medical image. Okay. Then this one is the original medical scan and this one is the enhanced medical scan. So this marks the original and this marks the enhanced medical scan, but I don't think so that this is really looking enhanced. Okay. Why? Because you have to manipulate this particular equalization. Okay. Here, a particular equalization is not happening. Then color conversion, you have to see another channel. So not necessarily you will be getting 100% results within a particular color space modeling. You just have to switch also sometimes. Okay, switching from A to B, from YCBR CR to HSV to any other color modeling also should also can be a primary target for us. Okay. So this you just try to see. Okay. In case you are not getting the desired results, okay, then that might be a thing. Okay. So this was regarding the practical aspects. Okay. Okay. Thank you all for joining the session. This marks the both of the things which I wanted to discuss. Okay. Both of the things which I needed to discuss within the present session. Okay. I have discussed the 10 particular questions along with that, I try to demonstrate what are the practical aspects, okay, and how the things are dealt, okay, that I have just demonstrated, okay. So be very, very careful with the practical aspects. Okay, I'll provide the link for the Google Colab notebooks as well as the link for the PDF already I've shared on the particular link. Okay, it has been shared here. Just try to see here. Okay, so please go through the link. Okay, please go through the recording. If any doubt is there, feel free to ask in the next session. Okay, and in any case, please revise. Okay, revise and repeat are the only two key aspects which can sail you through this particular course. So go through all these aspects. Okay, repeat, revise all the things, and be very, very careful with the theoretical aspects and try to expand your knowledge to the practical aspects. Okay, 8 weeks we already have completed. Okay, 4 weeks are left. Okay, so please start revising whatever the concepts we have dealt within from week 1 to week 7, week 8. Okay, and then afterwards we will just try to see within week 1 to week 8, within week 1 to week 12. After week 12 is done, then I'll be taking one another summary session of 2 hours in which I will be summarizing all the 12 sessions. Okay. So this is my plannings regarding these sessions. Okay, I have shared with you. Okay. So please feel free to just go through all these things. Okay. And all the very best. And thank you all whosoever have joined. Okay. Thank you very much. Do join the section next week, same time. Same way. Thank you. Thank you, Aaron. Okay, thank you everyone for joining. I'm ending the session for you all guys. Thank you so much.